Our next speaker is Marjorie Pomerole. She'll be presenting Invariant Detector, our automated way to find anomalies in write transactions.
Hi, everyone. So my name is Marjorie, as Ryan said, and I work on the security infrastructure team at Facebook in the London office. I joined the team in January, and I joined this very exciting project called the Invariant Detector that I'm very excited to share with you guys today. So let's first set up what really is the problem that we're trying to solve here. So at Facebook, we have different clients, our mobile apps, the desktop site, the mobile site, that talk to our servers over thousands of different endpoints. And they can talk to our servers over post requests, right? To like write to people's data, delete it, mutate it, stuff that we do at Facebook all the time. So at any given point, we have thousands of developers working on this code every day. And code gets pushed to Facebook at least 2 times a day, maybe 3 times a day. So we're really bound to introduce bugs. And that's the problem that we really need to think about. We're bound to introduce bugs that can potentially lead malicious actors to access people's data on an endpoint that is really not doing the right permissions check. So my team, the security infrastructure team, really wants to take care of this problem by building tools and frameworks so that our developers don't really have to think about security. It's just sort of in there for them. Of course, they still have to know that security is important, but we just make it easier for them so they can move fast and everything like that. So yeah, and everything's good. Let's think about these endpoints. So we have an example endpoint that can look like this, that updates a cover photo on Facebook. And we have some URI params. We might have the ID of the user, might have the photo that we're trying to mutate, and the cookies say that the logged in user is the same user that we want to change the cover photo for. That makes sense. And the code to handle this request might look something like this. You can get the user ID, the photo ID, you get the actor that's doing this request, and first of all, you check for permission, right? You want to make sure that the person that's logged in actually has permission to take this action. And you can go ahead, update the code, and everything's fine. So if someone uses curl to fabricate a request, changes the IDs on the user, the photo, or something like that, we're good, right? Like, the code is doing the right thing. This won't go through. All is fine. If at some point someone accidentally does some refactoring on this code and forgets to remove the permission check, this is really where we fail. Anyone can exploit our endpoints. They can do this action because we're not checking for permission. So that's the problem. So the first question we can ask is, OK, how we can make sure that these vulnerabilities don't go live in the first place? If an error like this happens, we're humans, we can spot it before it goes live. At Facebook, every single thing that we do goes through code review. So you can have, this is sort of like Fabricator, our open source tool to do code review. And we can, let's say, add our product security teams to every single code review that happens on the site. That would be great. They know what to look for. They know these problems. They can make sure everything's protected. But it doesn't scale because our product security team is a dozen people, and we have thousands of developers. So they really don't have time to look at every single code review. And we want to make sure that every time you're developing code, you move fast. And when you need to get something code reviewed, you can do it within your own team. You don't have to ask some overarching team that's looking down on everyone to make sure everything's protected. So OK, it's great. It's one thing, but it doesn't solve everything. The second thing we can do, and we do that, is add privacy frameworks. So at Facebook, we have these privacy frameworks that our privacy team developed that every time a product goes to talk to our data stores, it goes to a data fetching layer. In this data fetching layer, we run a whole bunch of rules. So there's a rule engine that figure out what the rules that it needs to run for this data fetch. And it makes sure that this data fetch can actually occur. So we send for the data fetching framework, OK, who's the actor, some details about the fetch, and it will make sure that, OK, you can actually go through. That's great. But this privacy framework still relies people, our developers, to go and manually add these rules. So we still have the problem that someone actually can forget to add the right rule. So again, it's a sort of bug, right? Same problem. And at Facebook, we have tons of legacy code. And the team has been doing like an amazing job of migrating all of our legacy code to use this data fetching framework. But the reality is that we still have legacy code that goes directly to our data stores and doesn't go to the framework. OK, so we still have vulnerabilities there. So OK, let's just think that it's just a fact that these vulnerabilities are going to be live. How can we find them if they're live before someone malicious finds them before us? Oops. Oh, I'm clicking the right thing. There you go. So we have this program called the White Hat program, which is our bug bounty program. I think Greg mentioned a little bit earlier. And it has been pretty successful. And we have thousands of people that are using test users. They're not like messing around with people's data to find vulnerabilities on our site. And they get rewarded for it if they find a vulnerability. And we found dozens of things. We've been able to patch them up really quickly. It's been pretty successful. But for every white hat that we have helping us, who knows how many out there are not there to help us. They're exploiting our endpoints even then, right? So thinking about these problems and seeing that, OK, everything we have is great, but is not enough, let's think of how can we take an automatic approach to this and make sure we can find what requests look like an anomaly, don't like look they're not doing the right thing. So how can we find them, block them, before they actually go and update our data stores? And this is what the Invariant Detector is. It's an automated approach to solve this problem. So what's the overview of the entire system, right? We have billions of requests going to our web servers. The Invariant Detector, the first step, is to get a sample of them. We need to know what's going on. So we get a sample. We log them to Hive, which Karen explained to you guys about. And we can log stuff like who's the actor, the endpoint, and something called the equivalent fields that I'm going to explain to you guys later. Then we have a data pipeline that runs, uses HiveQL queries to create a set of invariants. What it thinks about these types of requests, that it should always hold true for future requests. The third step is, because this set of invariants are created on a sample, we need to evaluate them before taking any action. We need to evaluate them in every single request that goes into the site to make sure that they actually hold true. Because when you're sampling things, there might be some endpoints that have a much lower volume than others, so you need to make sure that you actually evaluate them on every single endpoint. So you log those results back to Hive, and the data pipeline runs again, sees the evaluation results, sees the results you get from the sample and the set of invariants, and creates a new set that is like the ratified set of invariants. And those are the ones that we have 100% confidence that can be enforced. So we go send them to our web servers, and they can be enforced. So if a bad request comes in, we can block them. We have like a pretty high confidence by checking that request against the set of invariants that it's a bad request. We shouldn't let it go through. So let's do a deep dive in like each type of section of the system. So this is like so the equivalent fields. This is where the Invariant Detector really shines, and this is kind of like what it looks on our logs. Before we can understand this, because there's like ID 1, ID 2, what is this? I have to explain a bit about Tau, which we have a paper about that was released in 2013. But it's basically the API that every single product code at Facebook talks to before fetching data. So it's like a graph-based API. It's really optimized for read, but it works really great for Facebook the product because it represents everything into a graph, right? So this is like sort of how a subgraph may look like. You can have a user, and you would have an edge that's like the friend's edge to another user. You can have edges to the photo, like the photo that you like, and the photo also knows what people like the photo. And you can have unique edges, like for privacy settings and stuff like that. So that's how Tau works. And on these associations, you have two FB objects. We call the one on the left ID 1. We call the one on the right ID 2, and a soak. And each soak has a type. So if we think about the example that I gave at the beginning, You can have a user connected to a photo with an soak type of user to cover photo, right? And each object has fields. A user might have a name, date of birth, username. A photo can have an owner ID, the size, type, JPEG, PNG, stuff like that. So this is what the equivalent fields really are. It's just looking at all the values on these fields on both photos, both objects, and seeing like which ones are equal to each other. So you can have the value 2222 having a list of fields that have that value. So that's what we log. And another interesting thing that we look at is not just the fields of both objects. We also look at the environment of where the request is being done. So you can have a logged in user, which we call the actors. We are going to look at all of the IDs of the actors' friends, the pages that they admin, the groups that they have membership, the groups that they admin. And it's just a bag of IDs, right? The IDs of the friends, the IDs of the pages, the ID of the groups, and we can check them against all of the other IDs and all their values, it doesn't have to be an ID, that we see on both objects. So we can create a huge list of the values that are equivalent like this. So you can have like one of the IDs on the actor's bag of IDs needs to be equal to the owner ID of the photo, right? So this is what it is. It's really dumb, it's just like checking for equivalency, but that is really powerful as well. So after we log all of this information, everything is in Hive. The data pipeline is going to look at this. It's going to see which fields have been equal 100% of the time over a period of, let's say, 2 weeks. If that holds true, we can add this as an invariant. So for that type of a soak association, we can say that the logged in user always needs to be equal to the owner ID of the photo, which totally makes sense. You don't want someone else to, change your photo, your cover photo. So these are all automatic. Like some product person didn't have to say, this is how the product needs to behave. We put the Invariant Detector to learn this for us. So yeah, now that we have this set of invariants, we can send them to our web server. So when the request comes in, we can check it. And I really want to emphasize that we do this with very negligible overhead for every single write request that goes into Facebook, and this is really the important part. The Invariant Detector couldn't have been deployed if we're actually delaying the write request of Facebook. We don't want to impact the user's experience. But for that to happen, I need to explain to you guys a bit about how we do distributions of these rules and how they're stored. So we have these rules, and we have the problem of we have to send them to all of our web servers every day, because the pipeline runs every day and updates the set of rules. How do we do this? There is another system at Facebook called Configurator, which is a configuration type system to deploy these configurations across all of our web servers. You guys can check also the paper that got released this year, and I think that's a really great paper. And the way it works is when you want to update some config on the site, you update to a Git repo. There is a tailor that's going to see every time some commit gets added to that Git repo, and is going to distribute it. You can read the paper to see exactly how it works, but it's going to distribute it across all of our web servers, and it's going to keep these configs in memory. That's really important. We really need fast access to this set of invariants, because we're checking them synchronously, right? So great, we solved the problem of distribution and making sure that we get these invariants quickly with Configurator. But then we started thinking about, OK, Configurator actually updates a config in under 2 minutes. So every time you update a config, you're guaranteed to have that config updated across the entire fleet of web servers in under 2 minutes. Let's say oh, that was a slide. Can you go back one slide? That was a slide that was missing. Sorry. OK, never mind. Let's say there was a bad rule that got added, saying that, for example, the dimensions of a photo always need to be equal to some value. This is really, really bad. If we deploy this configuration to all of our servers and Invariant Detector starts checking the, add a photo to Facebook across that invariant, we have the potential of blocking every single photo that goes into Facebook. That's really bad. We don't want to do that. So the second thing that we started thinking about how to deploy these configs would be to use something at Facebook that we call the cache archive. And the cache archive is a binary of configs that gets built on every code push that we do at Facebook. And when the code gets sent to the webbies, the blob also gets sent and updated and loaded up into memory. So it's similar thing to configurator. We have these configs in memory. The difference here is that we do code push around 2-3 times a day. And every time there's a code push going on, there's always a number of engineers that are like more attentive than they usually would be to graphs and like what is going on the site because code is getting pushed. So if a bad invariant goes through and we can have like this grace canary period where first the code is going to get executed on, updated on 1% of the machines. And then it's going to be like a 20-minute period where the engineers can make sure that no bad invariant got updated. And if something bad happens, we can like remove that invariant very quickly or turn off the invariant detector if something really bad happens. That's a really important thing to take out of this. Always have a kill switch on systems like this. So if everything is good, you can just go through and update the entire fleet. Oh, go back one. Sorry. There you go. So this is really what the invariant detector aims to be, a system with negligible overhead that's going to look at every single request that goes into our site, and is going to be the very last safety net that we have available to prevent bad requests from going into Tau, which is our data store. So what happens when there is a violation? What happens when we saw that a bad request went through and we checked it against one of the invariants and the invariant detector said, OK, this is bad. It's going to, of course, get logged. And we're going to log all of the possible debugging information that we can have from that request. So who was the actor? If it was someone malicious, we can see what account they used, what was the endpoint, the stack trace, post data, all the possible information that we need. And then we send them to our product teams. And then there's a bit of a triage period where our team and product security look at these cases and tries to see, OK, what really should be the fix here? How can we patch this vulnerability? And how can we make sure that this doesn't happen again on the same product? And so the team, it's a really great working with the teams that they know that this is important. They take feedback from us, and then we can iterate quickly, and it's really great, right? But let's think about what if we created a rule, we send them to the team comes back to us and say, actually, that's not really true. This invariant may be true 99% of the time, but like for a very, very low volume of requests, that is not true, so we don't want to have this invariant. So we have a whitelist. We have a whitelist that one isn't stored in configurator, because again, if we want to update the whitelist with a rule that it's actually OK to have, like we don't want to block that, we wanted to have it updated in under 2 minutes, so we use configurator for this. So if a bad request comes in, we check it against we think we're going to block it. We go first, check it against the whitelist, and if it's in the whitelist, it's OK. We don't block it. It just goes through. And the great thing about the system is that it will log that this happened. It will log that we looked at the whitelist, so that for the next day, when the data pipeline runs, we know that that rule shouldn't be on the set of invariants again, so it won't get added. So everything is automatic, except the part that we actually have to add to the whitelist, which is not very frequent, but that's good. So some final thoughts. This is the cool part, some vulnerabilities that we found with the invariant detector and we blocked from happening. There was a request that was trying to upload pending photos to any album on Facebook in any specific endpoint in mobile, and we're able to block that. We actually blocked a white hat trying to exploit an endpoint that was scheduling draft posts in pages using our GraphQL API. There were some requests that were allowing personal photos of a page admin to be used on the page, and that ended up leaking the identity of the admin. So we're able to patch that up really quickly before anyone actually got hit by this. And there was an endpoint that updated location preferences on pages and was not checking that the person logged in was actually admin of the page. Again, the Invariant Detector prevented it from happening. And finally, what's next? What can we do to improve? As I said, there are false positives. And on a system like this, it's very important that we eliminate all the false positives because we're blocking people from actually writing to Facebook, deleting stuff from Facebook. So that's really a bad experience. We can add better tools to investigation so the product teams can know very quickly exactly what they need to patch up. And we can have better graph relationship support. So as I said, we look at the environment of where the request is coming from and what are the relationships that the user that made the request has. And we can just extend it to have better relationships. And that's pretty much it. If you guys have any questions about the system, please come find me afterwards. Thank you.